Hi, good morning everyone. My name is Enrico Santus and I am a data science leader at Bayer. Today I'd like to talk about a project that I've done together with the University of Udine and the Hong Kong Polytechnic University. This project is called COVID-19 Vaccine Opinion Analysis, and it is a project about monitoring the vaccines through Twitter analysis. So why is it important? Well, as you know, this pandemic has affected our society and actually tested the resilience of the healthcare systems, also the most advanced ones. So we needed in a way to get out with the vaccines. And we are assisting now at the biggest rollout of vaccines in the history of humanity. And of course, this rollout necessitates of monitoring what is the public opinion over these vaccines, understand whether there are fake news that may affect the decisions on whether taking or not these vaccines, so what is generally referred in the domain as vaccine hesitancy, and also create some information strategy, educational strategies to somehow educate the public to the benefits of getting vaccinated. So let me get into our project. My colleagues are mostly students from the University of Udine: Beatrice, Roberto, Eduardo, Simone. They are led by Professor Giuseppe Serra, myself, and Emanuele Chersoni. So the idea of our platform, which is what I'm going to present in a few minutes, is to provide insights that can be used by journalists, general public, or regulators to somehow understand what's going on Twitter. If you want to access our platform, you can simply go on the link that you see in the slide, and you will get in our website, and in this website you can interact with it and try to get those insights I will be talking about in the next slides. So how does it work? The system is organized in modules. There is one module that extracts daily the tweets from Twitter, and it gets the tweets that have some keywords related to the vaccines or some keywords related to COVID. When these tweets are taken, then they pass through a series of modules. One is trying to identify the location from where the tweet was generated, either by looking at where the tweet was generated or where the user is coming from. There is another module that is looking at the hashtags to understand which trends are somehow moving that tweet and the similar tweets. There are the URLs, so the analysis of the sources of information that people is using the most. And then a sentiment analyzer, which tells you whether a tweet is positive, negative, or neutral. This sentiment analyzer for the moment is simply based on the sentiment itself, but like it can be expanded in the future to see whether it's positive towards certain aspects. For example, is people agreeing with this policy? Is people disagreeing with this policy? Or is neutral? So it's a module that is for the moment there as a general module, but can be improved towards certain aspects. And finally, the most important module of the platform, which is the adverse event detection. Adverse event detection is crucial. Why? Because most of the drugs that enter in the market, in this case the vaccines, they are tested in clinical trials. But clinical trials cannot identify all the possible side effects because the population that participates to clinical trials is relatively small. So of course it's crucial to keep monitoring whether the vaccines or drugs are actually harming anyone, and eventually intervene immediately to reduce the harm actually. So let's start with the localization module, and then I think I will spend most of my time on the adverse event detection. So the localization module, as you see, is represented through a map that you see in this slide. And this map, you can see that part of it is in dark blue and part is lighter blue. The dark blue is telling you that most of the tweets are coming from that area, and you shouldn't be surprised that they are coming mostly from English-speaking countries, because initially most of the data we collected were from English-speaking countries, but we are currently moving towards multi-language approach. So in the near future, you will see this map a little bit more somehow darker, the darker blue more spread around. The second module was the URLs, right? So understanding which kind of sources people cite the most is crucial to see what kind of information is turning around. And here we have some insights that are very interesting. You see that the top 5 sources of information by the time I created the slides are very somehow reliable sources like USA Today, AstraZeneca, The Guardian, Sky, and so on. The reality is that after those 5 to 10 reliable sources, there are a huge amount of unreliable sources. And these unreliable sources, of course, have a smaller somehow public than the reliable ones, but they are many more. And being many more, they are actually much more spread and more capillary in the tweet group. So let's get to the adverse event detection, and I will mostly focus on this part of the platform in the next slides. So every year, dozens of drugs are released in the market, and pharmaceutical companies try to verify their safety in clinical trials, safety and effectiveness in clinical trials. So they are approved only once safety and effectiveness has been proved by the pharmaceutical company. But clinical trials are not sufficient to discover all potential adverse event detection. As I said before, for example, the drug-drug interaction cannot be somehow predicted because the clinical trials are too small to try all the possible drug-drug interactions. Why is this important? Well, it is estimated that adverse events account for 5 to 8% of the hospitalizations, and their number is increasing every year, especially the number of reports. Between 2008 and 2017, the FDA adverse event reporting system received over 10 millions of reports, 5.8 millions of which were severe, 1.1 millions of which were related to the death of the patient. So from these numbers, you can understand how important it is to monitor the side effects. And that's what we exactly wanted to do. But, you know, like the amount of data that is produced in a social media platform is increasing by the day or by the minute, actually. And it's impossible to perform this task manually. So NLP enters in the game, and it's very crucial. It has a very crucial role to allow our monitoring. The natural language processing community in the recent years has paid a lot of attention to this phenomenon, and they have created, they have organized workshops and created a shared task where people can compete and try to create the best model to identify the adverse events. So here you see in this figure there are tweets that get through a system. As the system is not yet described, and this system will identify the words that are relevant. Well, of course, this task comes with challenges. Most of the tweets are unrelated to adverse events. Maybe they can quote a COVID vaccine, or they can quote some symptoms, but neither the symptoms nor the COVID vaccine are somehow relevant to see the side effects. They may be mentioning something else. The other issue is that the tweets, as you know, are very informal, very short. They use slang, metaphors, and so on. So it's very hard, actually, for a computer that thinks in an analytical way to understand that kind of language. And finally, the various social media platforms use different text typologies. So you have the tweets that are short and noisy. You have the forums that tend to be much more somehow narrative and structured and so on. So we want to try to create a system that can work well on different types of sources. So the task of adverse event detection is generally performed through a NER, name entity recognition task, meaning that you go through every single word of the input data and you check whether that word is a drug or whether that word is an adverse event. And you see this in the slide. You see I took Adderall and now my head hurts. This is of course a fake example, just for the sake of a presentation. And you see that head hurts is the adverse event, where B stays for the beginning, I stays for internal part of the adverse event. So this is a typical way of tagging, which is called IOB label tagging. And the most efficient models in this domain are models related on BERT, which is a transformer-based model, which has achieved incredible performance in a large series of tasks, and adverse event detection is one of them. So these platforms based on BERT are actually generally very complex. They tend to use ensemble models, so multiple BERTs that collaborate with each other and so on. What we wanted to have was a simple model, and we wanted to look at BERT variants because we were assuming that some BERT variants may work better than BERT itself. And also it was crucial for us to work better in across sources. And we decided to go with SpamBERT. SpamBERT is an optimized BERT that instead of being trained to predict a single word, given the context around it, is trying to predict a span of text given the word before and after that span. For example, in the example you see here, Super Bowl 50 was, and then there is something that is masked to determine the champions. So you see that the mask part is predicted by the model, an American football game. So the system is trained to predict this kind of spans. And why is it relevant for our task? Well, first of all, because in adverse event detection, you don't extract single words, but you extract like spans of text. Like generally, people say my head hurt. They don't say headache. They may, but not necessarily. So generally, it's more words. Also, informal text tend to contain idiomatic expressions more than very medical specific words, and this is another reason. And the other reason is that the SpamBERT somehow favor the system to learn a more kind of a broader context rather than specific words relations. And in social media, this is actually very important, especially when you look at multiple types of social media text. So let's see the architecture very quickly. We use the SpamBERT followed by a CRF. So SpamBERT takes an input some text, it tokenizes it, and then it creates some embeddings. They are called contextualized embeddings. And these embeddings go through a linear layer plus softmax, which decides some temporary labels. Then there is the CRF. The CRF is a system that learns the transition between the labels. So it will try to harmonize this transition and then return the final labels. And this system actually performs well. We will show you the experimental setting in a second. We utilize two major source of data. One was SMMM4H 2019, which is social media mining for health applications 2019 shared task. And it consists of 2,276 tweets, which are short and informal. And then the CADEC, which is instead made by 1,250 tweets. Actually, sorry, forum posts, which are instead much longer and formal. We, of course, utilize several baselines, BERT plus CRF. Remember, CRF is for harmonizing the temporary labels. SpamBERT without the CRF, and then the top four models of SMMM4H 2014. And here you have the results. So what you see here is that SpamBERT plus CRF is actually performing better than all the other models. it's in 3 out of 4 cases. Particularly, you see the metrics for partial F1 score. The spam bear plus CRF performs always better, and in CADEC and the strict F1 score in CADEC. A little bit better in SMM4H for the strict, but slightly behind for the SMM4H partial, where BERT plus CRF actually performs better. So what we learned from here? We learned that the spans are actually very useful, and we learned that SpanBERT was able to extract the full span, while the other models tend to extract only a couple of words or one word that is part of the span. So that's why the other models are more competitive on the partial F1 score, because the partial F1 score will give you a hit even if you find only one of the words of those that need to be extracted. The system was sent to the SMM4H leaderboard and was ranked first in the period. I don't know now. I've seen this like a month ago, and 1-2 months ago, and it was that case. Maybe now there are other systems in the leaderboard, but what is important is that in February, with the system, we obtained the best IBM short paper. Yes, that was like an initiative, and we wanted to use these models and integrate to the platform that I was describing at the very beginning. So that's what we did. We did the integration, and then every day the system extracts the adverse event from the tweets, and it populates this word cloud that you can see here. So this word cloud is populated with the adverse events of all the vaccines. In this case, you see in the slide only 3 of them, but actually if you go on the website, you see all of them. And you can turn on or off different vaccines just to see, like, if you want to analyze specifically some of them. And you see the bigger the text, the more frequent is that specific adverse event. This was very relevant in the period where there were the discussion about AstraZeneca, Johnson & Johnson, about a cloud. Our system was able actually to identify very early some signals of these clouds, and it could actually see how the discussion on Twitter changed in the moment regulators intervened. So you can see really in the charts incredible changes in topic trends when the regulators intervene, and you can really identify the date. Very interesting, you may see also some sentiment changes in the period, if you look at the long period when news come out, or when some scientific paper demonstrated that vaccines were actually useful. So this system is actually helping us to have an understanding of what is the public opinion. If you click on one of the adverse events, what you will have is a pop-up window where you can actually see the tweets, the original tweets, with the information, and then they are colored in red or green or gray, depending on whether they are negative, positive, or neutral. And also you can see the agglomerated statistics, where you see which adverse events are more somehow correlated to a specific vaccine. And you see here, for example, the allergic reaction is more correlated to Pfizer and Moderna, while headache is more correlated to AstraZeneca. And so that's basically how the system is working, is providing insights on sentiment, sources of information, and adverse events. So while this system was generated only for monitoring tweet, it can be reapplied to any type of source data, whether they are call center or whether they are social media channels that belong to pharmaceutical companies or chatbots and so on. And once it's applied to that, it can be also generalized to new drugs over time. So it can kind of monitor adverse events for any type of drug, not only vaccines. So that's the power of the system. Of course, new training data may be needed, and it can keep learning over time and so on. But that's the direction we are going to take. This project is growing over time, and we would be happy to discuss about it. If you have any questions, feel free to ask it and to reach out to me. This is my website and my email address. So thanks a lot for listening, and looking forward to talk to you soon. Bye.